Hi everybody, welcome to the first lesson here, the fourth marking period. This is going to deal with section 8.1, which is going to introduce you to exponential functions. As we've done for the last several chapters, we've always started with the graphing aspect, and that's exactly what we're going to do here, which is talk about how to graph exponential functions, both growth and decay. So in this lesson here, a lot of this you're going to see split screen here with my graphing calculator. I would make sure before you get started here, having your graphing calculator handy so that way you can kind of follow along and press buttons as I do. As you're going throughout the video, obviously feel free to rewind and fast forward through whatever you need to. Once you kind of get a grip on how to do a couple of these, if you want to try one or two on your own and then kind of fast forward to see what you get, please feel free. Otherwise, sit back, listen, and follow along as I talk you through how to graph these. So, exponential growth and exponential decay are kind of like an offshoot of linear growth and linear decay. The difference is rather than having straight lines, we're going to have curved lines that go either upward or downward. So, if you see some of the vocabulary up at the top, again, a little bit more math speak with this, and we'll talk about how some of the numbers affect how things curve, where they shift, etc. But ultimately, you're going to use your graphing calculator to kind of do a lot of these different things. So why don't we talk about how we graph the exponential growth function first. So you can see in the box in the middle, what we call the parent function for exponential growth. This basically is a function that's going to start from the left, pretty much look like it's flattening out, and then swoop upward towards the right. So a typical exponential growth function is going to have an infinite domain of all real numbers. It'll have a limited range, and we'll also notate that with the interval notation you guys have practiced with in the earlier chapters this year. So you can kind of see what they're going to kind of look like here in the middle, but obviously the curve can be flattened, it can be sharper, just depends on the numbers that you're dealing with. So why don't we take a look at an example here at the bottom of the first page, y equals 2 to the x power. So what I'm going to do first is graph it on the graphing calculator, and then we'll talk through and actually plot it ourselves. So we go to y equals, we're going to do 2 to the x power, so 2, use your little caret, and again, most of you I know have the 84, so it should look very similar to what I have. Again, if you have an 83 or you're working off a different calculator, it might look slightly different, but ultimately use that caret button, as you can see in the key press history. Use that to get your exponent. But we're just going to go 2 to the x power, something simple. We're going to hit graph. And there you have a look at that exponential curve. So, you'll notice with your graphing calculator, it looks like it flattens out. Technically, kind of like with the fractional functions that we did a couple of chapters ago, they don't technically flatten out. It's just that your calculator can only compute so many numbers before it looks like something that it shouldn't. It's infinitely approaching an asymptote, which again, as you may recall, is one of those invisible lines that kind of cuts the graph off. So we can see here how it curves, and it's going upward from left to right. Let's take a look here at our table by hitting second and graph. Now, as I go and look at the x values, the more negative I go, you can see that the y values start getting smaller and smaller, but they get in smaller increments. And then ultimately you start reaching some scientific notation. That's what that E means, which means they're getting really, really small. So I'm going to go ahead and focus as the graph starts to increase. You can see it making pretty substantial jumps, and that's what exponential growth does. They make substantial jumps that aren't just a regular multiplier. It's growing exponentially, which means it's getting bigger, and then on top of that, it's bigger than bigger, and etc., etc. So when it comes to plotting these on your own, when you're making your own XY table, what you really want to focus on is where does the curve start to sharpen. Those are the ordered pairs that you really want to focus on, because then on one side of it, it'll either flatten out or shoot upward or downward, and same thing with the other side. So what you're looking for is a handful of points that'll show that curve, and then you can go ahead and plot those and then be able to make a pretty accurate sketch. So let's go back to our table, and you can see the table values listed here on the notes. This goes from -2 to +3. So we're going to go ahead here and plot that on our own, and then we're going to talk about domain and range. So we have, according to our table here, so -2, the y value is 0.25, -1 is 0.5, 0 is 1, 1 comma 2, 2 comma 4, 3 comma 8. So again, we're going to plot all these things here. And we'll straighten that out a little bit. And there is my exponential graph. Now, the other thing we're going to identify with this is our domaining range. Now, with these exponential graphs, the one nice thing about them is that your domains are going to go on infinitely. So you can see that the graph points left, and as you go towards the right, it's getting very steep to the right, but it's pointing right. As it continues to go up, it will always go to the right, slowly but surely. So we can identify our domain as negative infinity to positive infinity, using our parentheses on each side because you can never approach either of those. Now, the question is, what's our range? The range is going to be a little bit more limited because ultimately these graphs will only go either so low or so high, and we'll see that here with the decay, that it goes the opposite direction sometimes as well. But ultimately, if we look at our graph, our range can kind of be figured out by looking at our equation. So we see y equals 2 to the x. There's nothing attached to it, so essentially think of it as like a plus 0. Whatever is being added or subtracted to that function is going to be where an asymptote is going to occur horizontally. So in this case, since there's nothing being added or subtracted, there's going to be an asymptote at 0. If I were to scroll through my calculator table, if I look at the y's as I go more negative on the x-axis, we're going to have values that infinitely approach 0 but not quite hit it. So our range is going to go as low as just above 0. That's why we put our parentheses around it, because it's not quite hitting it. We can clearly see how high up it goes. It's pointing upward. If it's pointing upward, that means it's approaching positive infinity. So, using our calculator, that's how we graph. We plot our points. You've got your domaining range. And again, that information is going to come right from your graph or from the equation that you have. So, let's take a look here at a couple other examples. We look on the next page here. So this is where we start seeing transformations of that graph. So they're going to, again, be the same idea where you have something that curves. It's just a matter of, does it get a little sharper? Does it get a little flatter? What happens to it based on the numbers that are presented? So again, we're going to go through, we're going to graph them, then we're going to state the domaining range. So let's start with number 2. The one key thing about these, especially since you're dealing with exponents, is you want to make sure things are entered correctly. So you basically want to make sure your calculator looks just like you see them written out. So for 2a, we've got y equals 1/2 times 4 to the x. So we're going to use our fraction buttons here. And again, you can always type in 0.5 if that's easier for you. So there's 1/2 times 4 to the x power. All right, so we've got that. Let's take a look at our graph. So it looks pretty similar to what we had in the previous problem. The only difference is it looks like the curve gets sharper a little bit quicker, and that has to do with that 1/2 that's out in front of the exponential term. So it swoops up just a little bit faster than the other graph does. We go to our table. So again, I want to pick values that will actually show the curve of it. So I'm going to go ahead and range it from, we'll go from -1 to 1. Because if you look at this graph here, there's not a whole lot on the axes here. If you had more room, I'd probably go from -1 to 2. But again, as long as you have a handful of values that clearly show how it curves, your sketch will be good enough. So we're going to quickly write in an XY chart. So -1, 0.125, 0, 1/2, so that's 0.5, and 1, 2, because again, that's really all that'll fit. So this would be my graph. Now again, with the axes being modified, so you see this is only going from -3 to +3. Again, it's going to zoom in on just that part of the graph solely, but you can kind of, again, see where your function will be plotted. Domain, once again, it's pointing left and pointing right. Therefore, it's going to range from, your domain is going to go from -infinity to +infinity. Nothing is being added or subtracted to this exponential function, so you can think of it as plus 0. That means there's a horizontal asymptote at y equals 0. Therefore, your range would go from just above 0 all the way to positive infinity because it is pointing upward. Now we look at 2b. Same exact idea. So again, this is going to, as I keep flipping back and forth here, these will disappear. So make sure if you need to still jot this down or look at it again, hit pause here before you keep going. All right, so let's do 2b. So this one has more components here. So it has a 4 out front, so that's definitely going to affect the sharpness of the curve, times 2 to the x minus 1 power, and then minus 3 tacked on at the end. So that minus 3 is probably going to have an effect on the location of the graph vertically, because we haven't had anything added or subtracted yet. So anything, again, added or subtracted is going to shift the graph vertically. Anything that's out in front is going to move our graph, it's going to affect the sharpness of the curve. We now also see something affecting the exponent. That is going to also shift our graph horizontally. So let's take a look here at our graph. So again, it still kind of looks the same, but it's definitely moved a little bit on the graph itself. So let's take a look here at our table. So we can see, again, a bunch of y values that are kind of close to -3, and then we can start seeing they start making a nice increase here. So I'm going to pull, just so I can get a little bit more accurate of a sketch, and since they'll all fit, I'll go from -2 to +2 for my xy table. So again, make my xy chart. So -2, -2.5, -1, -2, 0, -1, 1, 1, and 2, 5. So we get all of our points. And we have our graph. Now, once again, we see our domain. It's pointing left. It's going to point right. Our domain is going to range from negative to positive infinity. The range is going to shift a little bit here because of this -3 that we have, this -3 that's attached to the end of the problem. So if you go back in your table and scroll through, you'll see a bunch of y values that start getting really close to -3. That's where that asymptote would be, and cut that graph off. So we would say the range is just above -3, comma, infinity. So that's what exponential growth is going to look like. So again, using your calculator to do the majority of this, but more to emphasize how we get domains and ranges, try to tie that back to some other types of graphs that we've done. But ultimately, that's what exponential growth is going to look like. It's a graph that goes left to right. Typically, that is increasing in value. Growth would be increasing. The other type is what we call exponential decay, which is when a graph will essentially decrease from left to right. So you can see at the bottom of this page, if you look at the bottom of the page here, you can see that what will show you that a function is exponential decay versus growth. Growth, you notice the value with the exponents if you go back through the first three problems. The value that's attached to the exponent was all above 1. That's what allowed it to climb up the way that it did. If you have a value attached to the exponent that's between 0 and 1, that is what will cause the function to show decay, and it will cause it to go downward from left to right, as you can see in the example below. So, what we're going to take a look here, again, you're going to see pretty much the same idea, except our graphs are just going to kind of be flipped around here. We're going to graph some exponential decay functions using the same strategy that I just showed you here in the first three examples. So, let's take a look here and do that. Alright, so we take a look here at the first example here on the last page. So it says graph y equals 1/2 x. So we can see the value that's attached to the exponent here Okay, that decay factor is 1/2. That's between 0 and 1. So that's going to be an indicator that it is going to go downward from left to right. So again, I'm going to type that in. Again, make sure that you are hitting all the correct buttons here. So we'll try that here one more time. Hit one too many things. So type in your 1/2. Make sure you're past your fraction here. You're outside of it. Raise your exponent. Now again, your calculator will make sure to, if you have the 84, it'll make sure to take all of 1/2 to the x. If you have an older calculator, you definitely want to probably put the 1/2 in parentheses like you would with most other things with fractions. Let's go ahead and take a look at the graph. So you can see how with that decay factor between 0 and 1, it's going downward from left to right. We'll go to our table. So you can see we have a bunch, as we go towards the negative x values, we get very high y values. As we start getting closer to 0 on the x scale, we start getting a lot smaller of y values. So again, I got a table here listed out for you from -2 to +3. So we're just going to go ahead and jot that in. So -2, 4, -1, 2, 0, 1, 1, 1/2, 2, 1/4, 3, 1/8. So again, I'm just quickly converting those to decimals because they tend to be easier to plot. So we'll plot our points. And we have our graph. So if I were to continue scrolling through my screen, as my x values get higher, I get y values that approach 0. Again, just like the examples from the first couple of pages. There's nothing being added or subtracted to the function, so that's going to give you an idea as to where it's going to approach without actually hitting. So there would be an asymptote in this case at y equals 0. So let's identify briefly here our domain and range. So our domain, once again, it's slowly pointing left, but it will continue infinitely on the left side. And it's definitely pointing towards the right. That's a lot easier to see visually. Our domain is going to be negative infinity to positive infinity. Our range is once again similar to what we just saw in the last few examples. The lowest value that it's trying to be is just above 0. And then it is pointing upward to infinity. Transformations that occur with decay graphs are the same as the ones that occur with growth graphs. So different things will affect the sharpness of the curve and the location of where it is on the x and y axes as well. So let's take a look at these last couple of examples here, plot them correctly, and we can identify some key pieces from there. So let's look here at number 2a. So we have 2 to the 1/4, times 1/4 to the x power. When you start throwing numbers in front of fractions with exponents, especially when you're typing in a calculator, I would highly suggest type them as you see them. If you make up your own symbols or you forget parentheses, it could potentially do different things. So please, again, type them in as you see them written. So 2 times 1/4 to the x, here's our graph. Okay, so we can see this really more affects the sharpness of the curve than anything else. It doesn't really look like it moves too much on the axes because there's nothing affecting the exponent. There's nothing being added or subtracted to the function itself, so it's not really shifting vertically or horizontally. It's just more the sharpness of the curve that's changing. So we'll go to our table. So we'll pick a handful of points here. So if you look at the way this graph is scaled, this is counting by halves if you look very carefully. So I'm going to pick, again, a handful that'll fit. So it looks like 0, 1, and 2 are probably my best options here. So we got 0, 2, 1, 1/2, and 2, 1/8. So again, with this graph being zoomed in the way that it is, it can kind of distort how you compare it to what you see on the screen. But once again, plot the points that you can get to fit. Pay attention to scales like you would any other graph. So once again, domain and range. My domain is just like all the other ones. It's negative to positive infinity. My range, very similar to most of these, there's nothing being added or subtracted. So this is going to bottom out at 0. It's going to try to approach 0. That's the lowest thing it's going to be. It's just above 0. And go as high as positive infinity. And with our last one, you can see there's more things occurring in our function. We've got something being added to it. We've got to the exponent. We've got something being subtracted from the function as a whole. So it's definitely going to shift a little bit more in our graph. So let's go ahead here and look at this last function. So again, make sure you type it as you see it. So we've got 3 times 1/2 raised to the x plus 1 power minus 2. Do a quick check here, make sure everything's typed in the way it's supposed to be. Looks pretty good. Let's go ahead and graph. So again, you can see the sharpness of the curve changes a little bit, and you can see that it definitely looks like it's shifted a little bit on the axes. Let's go ahead and pull up our table. So again, I want to pick things that are going to fit. So keep in mind, again, this graph, based on the one that I gave you here, is being scaled by halves. So negative 1, 1 looks like the first logical point, and then I can pick a couple others after it. So let's make our table. So we've got negative 1, comma 1, 0, negative 1/2, 1, negative 5/4, so it would be negative 1.25, and 2, negative 13/8. That is, doing some quick mental math here, negative 1.625. And that will be good enough. So again, we plot our points. Remember again, this graph is being scaled by halves. So we have our graph there. And now all we're going to do is once again identify domain and range. So for the billionth time, domain's unchanged here, just negative to positive infinity. And our range, again, this time we have something being added or subtracted to it. We see the subtraction of 2. So that's where, again, if you were to scroll through your table, you'd get really, really close to negative 2 on the y scale, but the graph doesn't technically hit it. So it's going to start at just above negative 2 and climb all the way to positive infinity. So that should be a pretty thorough explanation there on how to graph exponential growth and exponential decay functions. Obviously, we'll get beyond this and use a lot more in terms of algebra with solving exponents and their inverse friend, the logarithm, over these next handful of weeks here. So your homework that goes with this, there's a worksheet that you can practice on 8.1. You can see that in the Schoology folder. It is titled 8.1 Homework. That is, again, if you read all the other materials that I posted, homework is not being collected because I'm going to post the answers with the homework as I assign them on the day-by-day basis, so that way you can compare it and check your answers. What will be graded is the graded assignment that goes with this. It will be pretty similar because there's not a lot of mystery here with the graphing, but there will be a graded assignment that is posted with this. It says 8.1 graded assignment. You can try to complete it on the iPad, submit it, and do it digitally. You can copy it on another sheet of paper. You can print it however it works for you. You will need to submit that, though, by the beginning of next week. So if you have any questions on anything, again, shoot me a message, send me an email, or set up a video conference with me on Zoom if you really need some extra help. Thanks for watching, and we will see you next time.